Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today we are going to finish the lecture on MapReduce. We saw the logical model last week, and now we are going to look at the physical architecture of MapReduce. So you remember that logically, on the logical level, we have some input that is a huge collection of key-value pairs because everything for MapReduce is a key-value pair. We put things into key-value pairs no matter what, except Pokemons. That's the only exception, but otherwise everything is a key-value pair. Then we have the application of a so-called map function that is called on every key-value of the input. Then we take the output of this map function, which can be 0, 1, or more key-value pairs as the intermediate key values. We logically sort them and group them by key. Then we call the reduce function on every group. So all the key values with one key get fed to a reduce function. And then the reduce function outputs 0, 1, or more output key value pairs for every intermediate key. And finally, we get our outputs, right? So this is the logical walkthrough. And I gave you a few examples. I showed you how different inputs can be turned into key value pairs by hitting them with a hammer, like text files, text files that contain JSON or whatever they contain, it's still text. We have text files with key value pairs with a special characters that says what's on the left is the key, what's on the right is the value. We can read from relational databases where the primary key of every row is a key, and then the other columns of that row are pairs, so one key value per row. We can read from HBase as well, where the row ID provides the key and the content in the columns for every row provides the value. So is everybody with me on that? Who is with me? Okay, plenty of raised hands. So I had one last slide about the outputs. How can we write down the output of a MapReduce job? Well, you can choose. So the easiest is a text file. Just similar to how you read from a text file, you can write it back to a text file. Of course, that's assuming that you have a way to serialize all the keys and values to text. That's the assumption here, but there's a few built-in ways to do that. Then we have sequence files. Sequence files are basically an optimized binary version of a collection of key values. There are several things to say about this. The closest that you can think of as a starting point to understand a sequence file is H files. Who remembers H files in HBase, right? So it's basically just like H files. It's a file that contains plenty of key value keys. Key value pairs. But there is a small difference, is that in the sequence file, they are not necessarily sorted, right? It's just a bunch of key value pairs, but that's it. They don't need to be sorted. But the thing is, it's a binary format, so it's going to take less space, and to write and read back to Java objects is going to be very efficient. So why are sequence files useful? They are useful precisely if you want to execute several MapReduce jobs chained after one another. And that was the remark of one of you last week who said the output of the reduce phase of the first job is the input to the map phase of the second job. Well, if you want to do it efficiently, you should output the output of the first job as a sequence file and then read it back as a sequence file with the second job. Much more efficient than writing it and reading it as text, right? For whom is that clear, right? Now, we'll see that the sequence files are also useful for MapReduce to internally store the intermediate key values on disk, but that the user will not see, right? So it's also another use. Well, technically, there's another sort of file that are actually used internally. These are the map files. The map files are almost like sequence files, but they sort the content. They sort by key. So that's closer to an H file, right? So the difference between a sequence file and a map file resides in the sorting. It's not exactly an H file. There's a few subtle differences. One of the differences is that MapReduce might not actually sort by value. It sorts by key, but it doesn't really touch the values to be more efficient. So this is why I'm not writing H file here or saying it's the same, right? So conceptually, sequence files allow us to write efficiently and in a space-optimized way collections of key-value pairs, not necessarily sorted, and map files additionally sort at least the keys, right? Okay, and then finally, you can also, if you prefer, write it back to a relational database, to HBase, to other storage layers, and it's a bit modular, so you can also add more if you're an engineer and you like to build things, right? To whom is that clear? Okay, so these are all the ways you can read and write for MapReduce jobs, and with the sequence files, how you can chain MapReduce jobs to each other. Okay. So now we know how it feels from the user's perspective when you have data sitting in your data lake, S3, HDFS, HBase, and anything, and you want to map it, aggregate it, and produce some output that you put back on the data lake or some other data lake. But how is it physically implemented? This is where things actually start getting interesting. What I'm about to explain should also at least partially answer a question asked on the Moodle on the sorting of MapReduce. Once you know what's happening internally, you will get a feeling for what it means for the sorting. The short answer to the Moodle question is it depends, because you can actually tune it. But again, when I explain what happens physically, you will understand. So, as I said, there's multiple layers. You can do it locally on your hard drive, then it spreads across your cores. HDFS, S3, Azure Blob Storage. I'm going to take as the main example HDFS, because HDFS has the advantage of running on the same machines, as I will tell you, right? But it also works, of course, on other systems. So the idea is that you can run MapReduce jobs on terabytes of data and more, on thousands of machines. It's been tried on that many machines, even tens of thousands of machines, right? So you're talking about a lot of data, huge quantities of data. And a typical reason why to use MapReduce is because you have trouble reading the data from the disk on your laptop. Typically, even if you have small quantities of data that fit on your laptop, if you have on your laptop the problem that the disk is completely overloaded because it cannot read fast enough, then MapReduce is the answer, right? So that's typically what you use it for when the disk I/O is the problem. If your problem is the CPU, then that might not be the solution, MapReduce. Then you're talking about high performance computing, and like if you want to predict the weather or build climate models, then MapReduce is not what you should be using, right? So again, it's when we want to read from disk efficiently and we parallelize reading from the disk on thousands of machines, then we can read more bytes per second. For whom is that clear? Right, very good. So now, the architecture of HDFS, you remember, is centralized. We have a name node, process running on a coordinator node, and we have data node processes running on the worker nodes. We saw with HBase that we have exactly the same architecture with the HMaster running on the same machine as the name node, and the region servers running on the same machines as the data node. So it shouldn't surprise you that for MapReduce, we are going to do the same thing all over again, right? So we just need new names. Every time we need to give them names. So we are going to have a job tracker on the same machine as the name node and the HMaster. And we are going to have the task trackers that run on the same machines as the data nodes and the region servers, right? So far, so good. You just need to learn these two names, right? But the architecture is the same and the machines are also the same. These are just now 3 processes running on every machine, right? Okay. Now I have to say this is version 1 of MapReduce that works like this with job trackers and task trackers. There is a version 2 that we'll see in a bit that optimizes further. This is version 1, the first one. So the idea is that we have the task trackers on the same machines as the data nodes. That's exactly the same reason why we have the region servers on the same machines as the data nodes. The idea is that, as you can imagine, the task trackers, this is where the map function is going to be called on the data. And what this means is that the data is on the same machine where the map function is also going to be called, because the map function will be called all over the place. We call that bring the query to the data. The data is already here. It's sitting on the local disk, because you know that HDFS stores the files in blocks, and the blocks are eventually sitting on the physical disks on the cluster. So where's the best place to call the map function? On exactly the same machine where the key values are. For whom does that make sense? Right? So that's why it's designed in this way, and we are using the same machines in here. And we will see a lot of concepts that we learned from HBase will be useful in MapReduce. So that's very good news for you. I know it was not easy, the HBase lecture and so on. There's a lot of concepts, but you'll see it was worth it, because we will reuse a lot of the ideas, and then that will reinforce your understanding of these ideas. So now, in the logical walkthrough, I told you we have this huge collection of input key values, and we call the map function on every key value, right? Now, the thing is, we might have billions or trillions of key values. So if we would just read the key values from these one by one, and every time get the latency and then call the map function, that's going to take us years to read the data set, because every time there is a latency. What was the answer to this problem that we found in HBase? It's called batch processing. It's exactly the same idea. So instead of reading the key values one by one from the disk, we are going to read them in batches. What are the natural batches if we read the data from HDFS? What's a natural batch of key values? Yes? The blocks, exactly, the HDFS blocks. So every block of HDFS gives us one batch, right? So we take each one of the blocks. So I just put here 6 machines. I only put one replica for each block. You know that the blocks are replicated 3 times, right? But for simplicity, I just put one replica for each block. You should know they are also stored at other places. And so every one of these HDFS blocks is going to give us the batch of key values that we are processing. There is yet another name for that, even though I might have mentioned that it exists before. We call it split, right? So a split is basically a batch of key values that we will read in one go, and then we call the map function in every key value in that batch. So here we have 2 splits, 2 splits, 2 splits. So I roughly spread it. It doesn't have to be exactly 2 every time, right? Here I have only 1, here I have 3 splits, and here I have 2 splits, right? Again, simplified, I only put 1 replica for every block. So what we are going to have on the machines is, in addition to HDFS, we also have memory, and we have CPU. So this memory and CPU will be used for MapReduce, and we are going to have what we'll call later map slots and reduce slots, right? So a map slot and a reduce slot is just a bunch of resources on the machine that has some memory and some CPU cores, and whose only role is to call the map function or the reduce function repeatedly, right? So the map slot's job is to call the map function. The reduce slot's job is to call the reduce function, right? So now you notice that these map slots right here will read from the same machine. Super efficient. It can directly read it, this replica here, from the local drive, because it's sitting on the same disk. So these 2 right here, right? So it's the same machine. And on occasion, you might have a few exceptions. For example, in here, you might notice there's only 1 split and here's 3. So maybe this mapper will exceptionally read from another machine, transferring the data over the network for one of the splits here. Otherwise, it would be 3 here and 1 here, right? It's only just a small example to tell that generally it's going to be read from the same machine, but it doesn't have to, right? It can occasionally have remote reads. But MapReduce is doing its best effort to have most of the reads local, right, in the way that it spreads. And since there's 3 replicas, that makes it easier. 3 replicas of every block, so it gives us a bit of freedom to allocate the splits, the HDFS blocks, to the map slots. Who is with me? Right? Okay. Okay, so what's going to happen when we start the whole system? Of course, it's the job tracker that organizes the whole thing. Is basically going to instruct these map slots here to start reading the splits, so the HDFS blocks from the disk, one by one. And then for every HDFS block, it opens it, it reads it, it gets the key values from there, and it repeatedly calls the map function on every key value and keeps the intermediate data, the intermediate key value pairs, everything is a key value pair, in the memory, right? So at that point, all the intermediate key values are in the memory of the machine. Who is still with me? Right? Then, what happens if the, maybe I shouldn't have shown that immediately, but what happens when the memory is full and again, connected to HBase? What did we do when the memory was full in HBase? We had too many key value pairs in memory. What did we do? We flushed, exactly. We are also going to flush. That's exactly the same idea. The memory is full, too many key values, we flush them, right? And what do we do when we have too many files that were flushed on disk? We compact them, exactly. But we change the names. We don't call them flush and compact. Still, it's almost the same thing. We just call it spilled and merge. So you see, every time there's a new technology, the engineers need to find new names, right? But it's really the same thing. So we just need to get used to the fact that when we talk about MapReduce and not HBase, we are going to be saying that we spill all the intermediate key values, we spill them to the disk, and then we might merge the files on the disk, right? Who is with me, right? So normally that should make it easier because you already know what flush does, you already know what compact does, so we just do the same thing. But there is one small difference that I already mentioned. We might not sort strictly as in HBase, right? So typically by default, we might sort by key, but we might not push it so far as to even sort by values. But that you can a little bit configure, right? Okay, spill, merge, right? So now you start earning the benefits of having learned HBase, right? That we have some of the same principles. So that, of course, only happens if the memory gets full, right? Because if the memory doesn't get full, then we don't need to spill to disk and to merge, right? So that's when the memory gets full. And so again, I insist, we just reuse that exact same idea that we had in HBase with these log-structured merge trees that we flush, actually spill when the memory is full, and then we compact, we call it merge, when we have several files. It's a bit simpler than in HBase, of course, because in HBase, you're talking about weeks and months and years of flushing and compacting. In MapReduce, that's just for the duration of one job, right? So it's much simpler than HBase. You actually just spill as many times as you need when the memory is full, and then you just merge once at the end when you're finished with the block, right? So it's going to be a bit less intensive and complicated than in HBase. But that's the idea. So really connect, flush compact, spill merge, just the same thing from two different worlds. And then we have the shuffling phase, the one that I call the spaghetti phase, right? So at that point, we have the intermediate key value pairs. They're all in the memory of the machine, or if the memory was full, there might have been spilled to the local disks of the machines. And now that we are going to start the reduce phase, all of these reduce slots need to connect to every map slot to get the key values that they need, right? That are assigned to them. Right. So do you see that the complexity is quadratic here? Because every map slot will need to collect to every reduce slot will need to connect to every map slot, right? Because you might have key values from anywhere. Who agrees? Okay, very good. That's why we call it the spaghetti phase. That's why it's very intensive and takes a while because so many connections to do between the two. So the idea is that the map slots maintain their sorted lists of key value pairs, either in the memory or spilled in files on the disk. To simplify, just consider them sorted lists of key value pairs, right? I will tell more in a while. By value, it's a bit more fishy. You might not necessarily have the sorting by value later on, okay? Then, what happens is that every reduce slot is going to connect to every map slot and receive the key value pairs that are assigned to it. How does that work? We just use hashing, right? We have a hashing mechanism that hashes the keys, and with the hash of the key, you can say this is a reduce task number 1, reduce task number 2, reduce task number 3. So you nicely allocate the keys to the intermediate partitions, right? And when you have the hash, if the reduce slot says I'm interested in the 10th, in package number 10, in partition number 10, then the map slot is going to efficiently give all of these pairs because they've been hashed, right? Okay, who is with me? Right, very good. And then the reduce slot has all the key values that it needs to process. So the reduce phase can start, and the reduce slots are going to repeatedly call which function? The reduce function on every group. Every group that has the same key of intermediate key values leads to one call of the reduce function. Then we output the output key value pair, 0, 1, or more for every intermediate key. And what happens is that typically we write them to the disk, back to the disk, to HDFS. And here, what's going to happen, intuitively, you might have thought we just write it as a single big HDFS file, but actually not. We are going to write one HDFS file for every output partition. For every reduce task, we write one HDFS file. For example, it means that if this reduce slot who was responsible for partition number 10, it's going to create one HDFS file on HDFS and dump all of these output key values to that file. So it means that if you look at what's in HDFS, you're going to have a directory, an outputs directory that the user gave. They said, I want to output it to that directory. And then you are going to have numbered files, part 1, part 2, part 3, part 4, part 5, and so on. They have sequential numbers, right? In reality, it's more like part 00001, part 00002, and so on to have a fixed number of digits. But this is the idea, right? And of course, they can have different numbers of HDFS blocks. As you know, where is the one replica of each block stored by an HDFS client? On the same machine, right? You remember? So every one of these reduce slots is an HDFS client because they are writing to HDFS. So it means that they will store the first replica, one replica on the local machine, and two other replicas will go to other data nodes, right? So one local write and typically two remote writes through the data nodes pipelines. Who is with me? Right? So this is basically how things work in MapReduce. So this is what I meant with the 000. So this is what it typically looks like if you go to S3 or to HDFS after you have executed your MapReduce job, you will find this. I saw a raised hand, so I didn't react immediately. There was a raised hand over here. I think there was a raised hand. Was there not a raised hand? Okay. Don't hesitate if you have a question. I just realized that I saw one. Okay, then I'll just continue. But really, do not hesitate to interrupt me. Okay, so this is what the output directory of MapReduce is going to look like. So far, so good. Any questions? That's your opportunity to ask questions. Who has the feeling they more or less get how it works on the physical level now? Right? Okay, very good. So now I'm going to go ahead and introduce you an optimization, which actually was already mentioned last week because one of you asked about this. Because you noticed that for the Pokemons, we did not strictly map every Pokemon to a key value. We already pre-counted them, right? So the first persons who had the Pokemons, they directly saw, okay, I have 5 Pikachus, so I'm directly writing Pikachu 5. instead of writing Pikachu 1, Pikachu 1, Pikachu 1, Pikachu 1, Pikachu 1, right? So you see that's an optimization. That's called combining this optimization. You basically squeeze the intermediate key value pairs into less, but in a way that doesn't change the correctness of the results. And so the problem that we are solving is basically that we have the map slots right here. I'm not sure why it says mapper because I had changed that slide, but anyway. So I have here the map slots and here the reduce slots. And we want to reduce the amount of data that gets shuffled. You remember that this is called a push down, right? Who remembers the push down that I told you about maybe briefly last week? So let me explain this because that's a very general principle of big data. It is extremely important. It is not just for MapReduce. It is pretty much for any big data system. When you have a system that intensively processes data, it means that you're shipping huge amounts of data through the network cables. But the network cables have a limited bandwidth. So if you have a lot of data, this is just going to be slower. You might also need to read a lot of data from disk. And here too, you have a bottleneck because you can only read from disk that fast, right? And so there is a general principle of big data is that whenever you realize that you don't need all of the data, for example, you have a relational table with 10 columns, but you actually only need 2, then you're going to very eagerly get rid of the columns you're not using, right? And by very eagerly, that could even be all the way to when they are read from disk, right? When they are read from disk, you might immediately say, I'm only reading from this the 2 columns that I need. Who sees that if I'm using column-based storage like Parquet, where it's stored column by column on disk, this is going to be very efficient to just get the 2 columns I'm interested in. Who sees that? Right? That's the benefits of a column-based format like Parquet. And so that's called a push down. In that case, we pushed down a projection to just the 2 columns that we need. That is a very important optimization because not only does it need that you're reading less from disk, so you're going to need less bandwidth reading from the disk, but it also means that you are going to be shuffling less data because you're only shuffling the 2 columns now and not just 10 of them, diminished by 5. That is a push down. That's not the only push down you can do. That was an example of push down with projection, with Parquet files. You can only push down aggregations. You can basically do that by pre-aggregating. So the idea, this is what we did with the Pokemons. The idea is that instead of shipping over the network Pokemon Pikachu 1, Pikachu 1, Pikachu 1, Pikachu 1, Pikachu 1, takes a lot of network bandwidth, I'm just going to be shipping Pikachu 5. Right? And then I'm using less network bandwidth. So you can see that the amount of data that's getting shuffled is going to be much less than if I had sent all the key value pairs. Who is still with me? Right? Very good. And so the way that we are doing that is that instead of doing that one by one, the Pokemons one by one, we pre-aggregate, we push down the aggregation. If our intention is to count them anyway, we push down the counts and are going to give less of these key values. When do we do this push down with the combine function? So the combine function is basically some additional function that gets called during the map phase, right here. This is why I replaced mapper and reducer with map phase, reduce phase, which is more precise. So we are going to be mapping intermediate key values to intermediate key values. So the signature of that function is going to just, it's within the intermediate key values. We just call it to reduce a little bit the size right here. So that function is going to take Pikachu 1, Pikachu 1, and output Pikachu 2. When do we do it? Well, you don't have control over that. MapReduce just does whatever it wants. You can tell MapReduce, here's a combine function you can use, if that's useful to you. And then MapReduce might not use it, or it might use it a lot of time, but you don't have any control over that. But if MapReduce decides to use it, then if you think of it, when would it be efficient to use it? Well, maybe it would be efficient to do it when you spill to disk, right? Your memory is full, and you need to spill everything to disk. what better occasion to call the combine function and then spill to disk a bit less, right? Because you pre-aggregate when spilling to disk. For whom does that make sense? Right, very good. And then a second occasion is when you merge. So if you spill to disk like 10 times, and now you have 10 batches of intermediate Pokemon integer pairs, then when you merge all of these intermediate files to a single big file, you are also going to use the combine function to further reduce, I shouldn't say reduce to not overload the terminology, to further diminish the size of the intermediate data, right? Who is with me? Right. So now the benefit of the combine function is we have less to write to disk when we split and when we merge, and we have less to send over the network cables when we do the shuffling. So this is done with the combine function. So an example here is that I might have reduced with these ones all over the place. That's a lot of key values that get sent over the network. Instead, I'm going to push down the pre-aggregation, and then on the map slots, I'm going to diminish the number of key values by pre-aggregating in this way. And then only that gets shipped over the network, and then I reduce this, and the results are the same. It's very important that it doesn't change the results to do this, all right? Now, on the high level, the combine function is the user's problem. It's up to you, the user, to say, here's a combine function to you. So if you decide to provide a combine function to MapReduce, it is your responsibility to design that function in such a way that you know that it's not going to change the results. It's your responsibility. If you provide a combine function that is nonsense, then you're going to get garbage out of the MapReduce job. So it's very important to think about your combine function. Luckily, there is a very easy case where the combine function is very easy to figure out because you use the same as the reduce function. So there's many cases where the combine function is the same as the reduce function. But there's a few assumptions for this to work, three actually assumptions. When it is the case that the intermediate key value types are the same as the output key value types, which is very often the case, that's for example when you just aggregate the values, then that's the first assumption that you need to reuse the combine function as a reduce. Sorry, to reuse the reduce function as the combine function. It needs to be basically from one set into the same set, right? You just process intermediate key values. And assumptions 2 and 3 are that whatever you use to aggregate the values within the same key should be commutative and associative, right? For example, addition is commutative and associative. Counting is, if you use the sum, that's again, the sum is associative and commutative. You could use the max. The max is commutative and associative, right? The mean is commutative and associative, right? The average is not, right? You cannot do that with the average. If you pre-aggregate averages and then average again, then that's no longer going to give you the same results. Who sees that? Right? So the average will be a bit more involved. You would have to also add the weights to the intermediate key values to include the partial weights. And then with the weights, you can do a weighted average. It requires a bit more engineering in writing your function, but you can in principle do it, right? It's just a bit more effort. Now I wrote commutative and associative in quotes because technically a mathematician is going to scream if I say, you know, the reduce function is commutative and associative. No, it's not the function itself that's commutative and associative. It is what you use to aggregate the values together. The binary operator that you use to aggregate the values together, that should be commutative and associative, like max, min, or sum. For whom is that intuitive? That if you have a reduce function with the same input and output types, and that reduce function is essentially aggregating the values with a commutative and associative binary operator, then you can just use it as the combined function as well. Right? Very good. So that's basically in many cases. In the case of the sum, if we use the sum is commutative and associative, and that is the reason why we can pre-aggregate using that exact same operator. That's 80% of the cases where you can just do that. And in the remaining 20%, you just need to think of it more and sit and design and then write down your combined function in a way that, that doesn't change the correctness, right? Do it as an exercise for the weighted average. Imagine that your goal is to compute the overall average per key. Try to come up with a design for the format of the intermediate key values and what your combined function and your reduce function could be for doing that. It's a very good exercise to try to figure it out, because that's not going to be this simple case where you can just reuse the function. Okay, and again, that's this idea, very important, of the push down. You push down a projection, you push down a pre-aggregation, you basically just to very early pre-aggregate or project away the data that you don't need to reduce what you need to read from disk or what you need to write to disk or what you need to send over network cables or even what you need to have in memory, right? Very generic principles, not just for MapReduce, but generally in every big data system. Who has already pushed down some optimizations? Not so many. Right? It's a very good idea. Later, when you work for a company and you see it's taking too long a time, sit down and see if some of the data you're shipping over the network cable might be useless, and then you can just project it away very early. It's magic. That's the easiest optimization you can do, and it really pays off in terms of performance to do these sort of things. All right. Plus, it's intellectually very satisfying to engineer that kind of solutions. Any questions so far? Yes? Maybe the microphone?
Thank you. Do we also already apply the combine function during the spaghetti phase? Because then we wouldn't need n² network connections, right? We just merge them whenever they connect, then we could do the whole spaghetti phase and log n.
Ah, you already figured out MapReduce version 3. So that's a very good idea. You could imagine that kind of optimizations. If I correctly understood you, what you're suggesting is that the map slots would basically communicate with each other in order to pre-aggregate across machines, like a tree. You basically do a tree of map slots, and then you pre-aggregate in this way. I think it would be worth trying. You know, I don't know if anybody tried that. That could be something to be tried. And then, of course, you would need to run performance measurements and to see if doing that helps, because of course that introduces an overhead, right? Because the machines need to connect to each other a bit more. But if you manage to do it logarithmically, maybe that's the sort of things that that could be tried out, right? I don't think MapReduce does that, but that's not an idea I would discard, right? Maybe that's something to be tried.
Okay, thanks.
Right? All right. Other questions? All right, but that's very good thinking, because you're the engineers of the future, right? You will be the one who will invent the new products that are even more efficient and at these things and solve new problems. Okay? Or you just want to get back the microphone? I thought there was another question. Okay, so now just about the API. The native language of MapReduce is Java. So the most natural way to write your jobs is to implement them in Java. But there is also a trick to do it in Python or other languages. The trick that it uses is that instead of implementing function, you basically use the pipes on the command line. You basically read, a map function is written in a way that reads from standard in and writes back to standard out, like as a script. And then it's used by MapReduce to run it, right? I'm not going to go into it. Just know that it exists, that there is this way to do that in other languages like Python, using command line pipes style scripts. But anyway, in Java, I'm going to scare you just for a few moments with some Java code, but just so that you see what it looks like, just a signature, right? So you basically design a class. The name of the classes is the only permission you have for saying mapper or reducer. You can call your Java classes this way, but otherwise do not use this. I'll come back to this. But basically the map function, unsurprisingly, takes one key and one value and you can call context write as many times as you want to output 0, 1 or more intermediate key values, right? For whom does that make sense, right? This signature? Very good. So you saw it concretely. I take one key value and I output my intermediate key values. Then the reduce function, remember that it's key values with the same key. So we only pass the key once. That's a small optimization. So we pass the key, and then we have the values in here. And again, to optimize a bit, it's an iterable. So it's basically just some kind of structure that you can stream your way through, right? With next has next, next has next, you just iterate. So iterate through the values and execute it, evaluate it for every key, for every group of key values with the same key. And then again, you just call this context write 0, 1 or more time to output your output key values. Who is with me? Right, so that's the signature of the reduce function. And if when you set up your job, you just say, this is my map function, this is my reduce function, this is my input path from HDFS, this is my output path to S3. I give it a name. You can give it a name if you want to, just like to your cat or to your dog. So let's call it word count. And then you wait until it's done, right? That's in principle MapReduce job in Java. If you want to add a combine function, it's easy, just add it here. Just add the combine function. You need to write a class. Of course, if you just reuse the reduce function as the combine function, then just reuse the same class, right? Then it's easy. If it was just computing a sum or mean or max of the values, then you can just reuse it like here. Otherwise, you need to write it yourself. You can call it my own combiner, and then you write it down. Who is with me? Right? Very good. So I hope that little bit of Java code didn't scare you too much, but now you see the signatures and the way that these functions look like. Now, I have a conceptual part that is very important to bring your understanding of the architecture to the next level. If you look at the internet and ask for explanations about MapReduce, you will see that plenty of people say mapper and reducer and combiner, mapper, reducer, combiner, and so on. That is not precise. Because when you say mapper and reducer, you don't really know what you're talking about. Are you talking about the CPU? Are you talking about a partition? So let me give you very precise terminology that will make it clear in your mind what's actually going on in MapReduce. So I'm going to tell you to say map slot, reduce slot, map task, reduce task, map function, reduce function, combine function. Right, so do not ever say mapper, combiner, reducer, except for the names of your Java classes. That's the only exception, okay? In order to explain that to you, I have a concrete example from real life. Imagine that you went to vacation with a couple of friends and you need to write a lot of postcards to your many friends, and you need to organize yourself. So in that case, we have 50 postcards to be written, and we have 3 groups that we made here. And we need to basically organize things in a way that's efficient. So first, these people know about batch processing, and that if they do it postcard by postcard, it's not very efficient. So they are going to batch the postcards in piles of 10 postcards. So they already prepared the 5 piles of 10 postcards each. And every one of these piles is called a split. And every split is associated with a task. A task is a to-do, right? So the task number 1 is to write something on the first pile of postcards. We have 5 tasks that are there, that are things that need to be done, which is writing words on split 1, hopefully that are nice and that make sense and that you want to send to your friends, maybe stamp the postcard and write the address, right? So these are the 5 tasks. So what's going to happen now is that each one of these 3 groups takes a task each. So tasks 4 and 5 are left aside for now. And they start writing on the postcards and putting the stamp and writing the address. Of course, Alice in the middle got a little help. So she's going to be finished a bit faster than everybody else. So what she does when she's done is that she takes another task, right? So what we notice here is that there's multiple tasks done by every group, right? So multiple tasks by every slot, right? So then maybe who is done next? So Bob is done and takes task 5. Then Mary over there is done, but there's nothing less to do. So she becomes idle. She doesn't do anything anymore. And then everybody waits until everybody is done. And that's how we organize the tasks. Right. After the break, I will explain to you what that means concretely for the cluster of machines. But having this picture is going to help you. So let's get some coffee. I'll see you in 15 minutes.